Hi everyone, we are Team Happy Egg, and our team members are Zhu Junshen, Kai Wen Yang, Ben Xiong, Hannah Han, Justin Tian, and Daisy Du. So our project is about machine translation, and you could find the links to our blog post and GitHub repository at the bottom of this slide. So I'm Daisy, and I will start with introducing the background and challenge of our project. Then Zhujun will give a description of the data and show how we preprocess the data. Next, Kevin will introduce the RNN model and related techniques, and Justin will demonstrate the GRU model. After that, Ben will introduce the LSTM model, and in the end, Hannah will talk about future improvements. So now I'll give a brief background of our project. Significant areas of Chinese speaking are not limited to China, and other countries with significant Chinese speaking populations include Singapore, Indonesia, Malaysia, and Thailand. And due to a large number of native Chinese speakers coupled with increasing popularity worldwide, Chinese is the most spoken language in the world. And needless to say, another popular and important global language is English, thereby making Chinese English translation tools especially important. So the 6 main translation platforms we currently use are Google, Tencent, Sogou, Youdao, Baidu, and Bing. The creation of machine translation has vastly facilitated communications between people of diverse backgrounds. And while different machine translation tools contain disparities in their performances, we delved into Chinese English translation machines to create our translation machine models, and we evaluated their performances. So the translation between Chinese and English is more challenging compared to that of other languages. And first of all, the linguistic units in Chinese lack systematic correspondence to those in English. For example, there is no spacing between words in Chinese, while words are separated with spacings in language systems like English. And in this case, a word-to-word translation may not work. And secondly, deviations in translation may take place due to different sentence structures. And last but not least, sentences may change in length after translation. So take the sentence, the final project is due tonight, for example. After translation, the words due and tonight are in reverse order, and the words the and is are neglected. Next, Jujun will take it on from here to provide data descriptions and to explain how we preprocess our data.
Hi, I'm Zhu Junshen. Now you have known a little bit of our project's background. Next, I will further introduce our data through the data description and data preprocessing. The dataset we will be using is from the corpus, which is an open source online. There are 2 million English-Chinese parallel corpus, altogether covering 8 different text domains, including education, laws, microblog, news, science, spoken, subtitles, and thesis. In this project, we use data about news only, and this is what our original data look like. You can find one English sentence followed by its Chinese interpretation. Like what is mentioned by Daisy earlier, we have to do text segmentation before any real analysis. English text segmentation is very straightforward. In each English sentence, we can find all English words isolated by space. But what should we do about Chinese sentences? There is no space between letters. Also, one word can be formed by one or multiple letters. For Chinese speakers, we can easily segment sentences by looking at them, but computers can't. Wrong segmentation may cause jokes. For example, the following sentence means, they carved up our land. But if applying the wrong segmentation, it can also mean, they took our sweet potatoes. There are 2 approaches we can use. First, we can separate every single Chinese letter. The histogram here shows the top 10 letters in both language with the highest frequency. This is feasible but inefficient because it causes extra calculation when multiple letters should be combined to form one single word. There are multiple build-up modules we can find online to solve this problem. We choose to use Jieba, one of the best Python Chinese word segmentation modules. After Jieba, we notice that the top 10 frequency word does not change much because these words consist of one letter in the first place. However, If we plot the histogram for the top 10 words with multiple letters, this is what we got. The number is quite large. Apparently, by using 结巴, the model can be improved tremendously. Compared to these top 10 words, there are many special nouns or large words that appear very seldom. Thus, we replace all less frequent words with a single token unknown to avoid unnecessary calculations. An interesting fact, if we plot the log rank versus log frequency for the top 10 words, we can see that Zipf's law holds. Besides word operation, there are two steps of sentence operation. First, we need to make change to the input so that the machine can handle different sentence length. We put the start token before every sentence in both language, which can be considered as a pointer for the model to start training. Similarly, we put the end token after every sentence. Next, in order to train in batch, we pad or shrink all sentences to one length. In our case, 100 for English and 200 for Chinese. After these, we have to transfer our current data into the type that computers can understand and operate, which is also known as embedding. Word embedding, similarly, can be considered a mapping function that turns words into vectors. Similar to one-hot encoder, it creates a unique vector for each word. Moreover, those vectors follow some rules such that they relate to each other in certain ways. In addition, if we have a big data set, say 10,000, by using one-hot encoder, we will need a 10,000 dimension vector. But with the help of embedding, we can use a few 100 dimensions instead. Thus, in our project, we use embedding on the dataset that has been processed by 结巴. This is all for data description and data preprocessing. Next, Kaiwen will give a brief introduction about some more technique we is about to use in this project.
Hi, I'm Kaiwen. I will be introducing the ideas about RNN, encoder-decoder model, and attention model. Our model is based on recurrent neural networks, which is also called RNN. And RNN works similarly to a fed-forward neural network, except it also has a connection pointing backward. As we can see from this graph, each neuron in an RNN would receive an input and then produce output and sending the output back to itself. Therefore, the model has a form of memory about all inputs in the previous time step, and those memories were stored within a function called hidden state. In this way, since the last word of the sentence can affect the first word of translation, the model needs to see the whole sentence before translating it, instead of translating every single word. This is why we use RNN in machine translation, because when we're processing sequences, we want the model to have a memory about the whole text instead of just focusing on one particular word. Machine translation is essentially training a sequence-to-sequence model. For different languages, the length of sentences can be very different, even they have the same semantic meaning. Therefore, we mainly implemented the encoder-decoder model to solve this problem. It transformed the text input into a vector, and this vector contains information on the semantic meaning of the sentence we are translating. Then this vector will be fed into the decoder, which is a vector-to-sequence network, and the decoder will transform the vector into a sequence in the language we want. This graph in the middle shows the basic architecture of an encoder-decoder model. The shortcoming of this model is that the length of the vector generated by the encoder is fixed, which means sometimes the vector is not able to store all semantic information of the original sentence. Therefore, we try to improve our model by implementing an attention mechanism. Basically, how it works is that every time it makes an output, the model would know which part of the input it should pay more attention to, and then the model would focus on those parts when it is producing the next output. In this way, the model will focus on a certain subset of the input sequence that contains enough information for translation. So the third graph over here shows the difference between an attention model and an encoder-decoder model. So that would be all for the basic concepts about neural network we are using. Then we'll introduce how we use these techniques to train our model in the next part.
Hi, this is Ben, and I want to talk a bit about the baseline model that we used. Our baseline model is quite simple. We used an RNN with a single dense layer as its cell. It concatenated the inputs and the old states, and generated a new state which simultaneously functions as the output. This model is our baseline model. Unsurprisingly, it doesn't perform well due to the lack of complexity. We want to reiterate here that an RNN is more of a structure than an actual fixed model, in that the structure of each cell has decisive impact on how the model performs. For the dense layer, information is lost as the cell processes sequential data, because the last few inputs naturally have more of an impact on the final result than the first input. And with a long enough sequence, it's almost impossible for something right at the beginning to affect the final output, which is a long way in many calculations ahead. This is an example of what the baseline model is capable of doing.
Hi, this is Justin, and thank you, Ben, for giving us introduction to the baseline models. And I'm gonna talk about GRU models in my section. So RNN is a good model usually when we tackle problems of natural language processing, but it also has a huge drawback. So if the model is too complex, if there are too many layers, when we do backpropagation, we might have a problem of vanishing gradients, and the earlier layers might be too slow to train, and they may not learn anything, and the earlier inputs might get forgotten. And to solve this problem, we introduce LSTM models. So long short-term memory models have several gates to decide what information is important to carry on and what information is not important, so that we can ignore it. And LSTM models improve the performance for sure, but there's also a problem. As the model is a little complex, the training process could be a little too long. And to solve this problem, we introduce GRU models. So gated recurrent units have fewer gates than LSTM models, and they just have two gates, a reset gate and an update gate. The reset gates could decide how much of the past information to forget, and the update gate could decide how much information to forget and how much new information could be added. And with fewer gates, GRU could facilitate the training process. And if the data set is not so large, the performance of LSTM models and GRUs could be close to each other.
Thank you, Justin. This is Ben again. We want to talk about some of the more complicated models that we used. Here, we replaced the cell with a more complicated GRU cell. As we've explained previously, GRUs are designed to solve the aforementioned problem with dense RNNs to a certain extent. With a cell state, GRUs are capable of retaining information from longer in the past. We also tried a little trick to improve overall performance, which was to connect the input and target sentences together and form one big sentence, separating its two components by a start translation symbol. Without this, the old architecture was only capable of training on information provided by the first language, and using the comparison between predictions and target language as DOS. This process allowed labels to be included as training data, as long as we carefully control the displacement of the words so that every prediction has no access to the future labels. Now, this model was capable of providing reasonably good translations, meaning-wise, although its diction and grammar are still quite limited. Also, this model would repeat a lot of its words. Finally, when training with larger datasets, we used LSTM, which is a more complicated version of a GRU, but with the same basic idea. The results come out as expected, and we believe that further implementation with LSTMs of their current structure is very much possible.
Hi, this is Hannah. Now that Ben has introduced what we can get by using GRU, I'm going to talk about the result we got using the LSTM model with attention layer developed by Facebook AI Research Group and published in the FAIR-seq library. So for the whole training dataset, Chinese input has over 170K in vocab size after Jieba segmentation, and English target also has a large vocab size, but only 5,000 tokens from the input and output will be kept due to computing power limitation, and the embedding size is 512. Looking at the implementation code of the encoder, we can see that there is an option to load in pre-train embedding layer for the model. Since we did not provide any embedding files, we actually trained embeddings from scratch. So here comes some interesting interpretation results. When the ground truth should be protection of animals, our model actually produced protection of civil society. Because the phrase civil society usually follows protection of, and civil society is kind of related to animals because it's human community anyway. And another example is that when a ground truth is I would like to travel or I want to travel, our translation is I would like to tourism. Apparently, our model has not learned that like to cannot be followed by a noun. And this translation got a blue score of 0.669 out of 1. Model for 1 day on a small training set. Let's see how it performs. So the English translation output on the validation set is scored against the reference text, and I got an average score of 26 over 55,000 sentences. And let's see how it performed on a particular example. So when the correct translation should be at a time of increasing awareness of the need for international agreement on something. The translation is in the current broader understanding of the international community, and the European Council is willing to share the experiences in the development and blah blah blah. Okay, so this is actually looking good. And European Council of Europe in the area of development and implementation. So I don't know what this mean here, but overall I can get an understanding that in the current situation, European Council is trying to do something. So the future work is that the first thing we can do is to increase the vocab size coverage from only using 5,000 tokens to increase the coverage ratio to over 90%, and also train on the full political topic dataset and an informal dataset that's the news topic dataset. Try to train for longer, more epochs, and try a character level model and convert Chinese characters to Wubi encoding. So more about Wubi encoding. So it's a shape-based encoding for Chinese characters. As you can see that it's based on the stroke when we write the Chinese characters. And every unique Chinese character has a unique Wubi stroke, even if their pronunciation are different. So the author of the paper Character Level Chinese English Translation proposed that converting all Chinese characters to Wubi and use Wubi as the input of the model will produce much better, a little slightly better result. And also using Wubi will largely decrease the size of the token vocabulary to only containing 128 ASCII characters. Finally, thank you for listening to our screencast, and hopefully you find our work helpful.